All right, so now we're going to look at deriving the state space model for the mechanical system here, the spring mass damper system. And we're going to treat f of t, the input, as an input, and it's the force, and the mass displacement s of x of t as the mass displacement and the output. All right, so the input to the system is the force f of t, and the output to the system is x of t. Now, we discuss the equation f of t minus c dot x of t minus k x of t equal m double dot x of t. And so that is Newton's law, which speaks to the resultant force in a system or on a system, and the and in terms of its acceleration, right? So resultant force is equal to mass times acceleration. Now you will recall, and you should recognize rather, it's the differential equation. Okay. Now, whenever we're going to define a state space model, we need to find the state variables. All right. And I'm reminding you now that the state variable is the smallest set of linearly independent variables, such that if we know the values of these variables along with the system input, we can completely define the system's behavior. Okay, so if it is that we now need to derive a state space model for this system, the first task at hand is to determine or to establish the state variables. Now, I want to remind us that when we speak about a first order system or a second order system or a third order system, we are speaking to the order of the differential equation that describes that system. So a first order system would be defined by a first order differential equation. Same for second order. Second order system will be defined by a second order differential equation. Okay, and it goes on, third order and so forth. So in this case, can somebody tell me what is the order of the system?
Second order.
And why is that so?
Because you can see the two dots on the over the x.
So the highest derivative term in the expression is double dot, which is the second derivative, and that would be in fact correct. Thank you. So it's a second order system. And I would have said to you that the order of the differential equation defines the number of state variables. So with a second order system, you're going to need 2 state variables. A third order, you need 3 state variables. So right now, we know we need 2 state variables. Now, what I'm going to propose here is the method for finding the state variables. So we're now selecting, right, the state variables by choosing what? We're choosing the system output, yes, which is the mass displacement, as the first state variable, and the first derivative of the mass displacement as the second state variable. I'm speaking to what is happening right here. Okay, get my pen. So I'm speaking about right here. Okay. All right. I'm sorry. I'm speaking about right here. Okay. So x1 of t, first state variable, is x of t. And remember, x of t is the mass displacement. And our second state variable is the first derivative of the system output, which we know is the mass displacement. Therefore, we're differentiating x of t. And by so doing, we have x dot of t. All right, so let's go back one more time. Here we're selecting our state variables. Simple way of doing it is to choose the output as 1, and the other state variable is the derivative of the mass displacement. What are those 2 variables actually equal to? Of course, the first one is displacement. And the other one is what? As a variable. What is it? Go ahead, Richard.
Sir, are you recorded?
Yes, I am.
Okay.
That's your question? Right,
Yes,
so I'm
sir. Go
asking
back.
now, the first state variable is the mass displacement. The second state variable is what? In terms of a general variable, it would be what? Velocity. Are we seeing that? And velocity and displacement are two independent variables. Kindly mute your mics, please. Thank you. All right, so here we have just selected our two state variables. Now, the next move would be to write our expression in the format that the state space expression looks like. And you recall that the first are the static, which is actually x dot, the first derivative of the state variables. Now the way to write it is like this. Here we have two state variables, x1 dot, x2 dot, equal, and we continue. So if we bring our attention over here, we have x1 dot. What are we doing? We're differentiating the x1 term, okay? So we're differentiating the x1 term, and what we end up with is x of t raised to the power, well, not to the power, I'm sorry, the first derivative of x of t. Are you with me?
Yes.
What we're doing is to differentiate both state variables because we know we want to end up looking like this. This is our objective. This is what we want. So we have to differentiate both state variables. When we differentiate x1 of t, we get x dot of t. Here we are. But we also know that x dot of t is a state variable. It is actually x2, and so we put that there. Let's now move on to x dot 2, right? Or
When you,
x2
di-
dot.
when you differentiate x1 of t, you get x dot of t.
Could you repeat, please?
You just said a while ago when you differentiate x1 of t, you get x dot of t.
Mm-hmm.
But that's not what I said there. When you differentiate x1 of t, what I'm seeing there, you get x of t unless you forgot to put the dot.
Are you seeing right here? Are you seeing equation 2?
Yes.
Or what? Read it for me,
But
please.
I'm seeing that x1 equal that x of t equal x2 of t.
Mm-hmm.
But
Right.
initially you said that x when you differentiate x1 of t, you get that x of t.
What's wrong with that? Remember, x1 is all right. Look here. Up here, I have x1 of t, and bear me with the x's because that may be the issue at the moment. They're all time functions, but here I did not put back the expression of time in the function. So x1 dot or x1, well, x1 dot of t is the same thing right here. Are we seeing that? All I'm doing essentially is I'm taking, let me erase this. I'm taking this component here and I'm differentiating both sides. What would you get when you differentiate both sides?
As I have it below, you will get that x1 equal that x of t.
Okay, so that's all I'm really saying. But by extension, I'm saying we know from over here that x dot of t is x2. Do you agree?
Yeah.
All right, so basically that's what I'm saying. All right, so let's move on now to x. We're differentiating the both sides over here as well. This becomes x2 of t dot, you see it right here, is equal to double dot x of t. Now, we have to now examine, is double dot x of t a state variable? You can go ahead and mute your mic, please, if you have no further questions or comment. Getting a feedback. Is double dot, is this? Let's write it. Double dot x of t. What's that? When you differentiate this expression here, you're gonna get x2 dot of t equal what? X double dot of t, which is actually equal to what? Acceleration. The question I need to ask now is acceleration a state variable? The answer is no. It is not a state variable. Therefore, we have to replace that variable and represent it in terms of what? State variables and input. In the first case, in this case right here, we didn't have to do much work because x dot of t is in fact a state variable. Okay? Go ahead with the question, Richard.
So initially you had said velocity is a state variable, right?
It is.
What made you determine that velocity would be a state variable and acceleration not?
I'm sorry? Go ahead, please, with the
What made you
question.
determine that velocity is a state variable and I'm saying what made you determine that velocity is a state variable while acceleration is not?
You could have chosen it to be. You could have chosen displacement and acceleration. It would work. That is why the state space model is not unique. However, the analysis or the result of the analysis will yield the same dynamic representation. When you model the system, it will give you the same output. Okay, so the selection of state variables will determine the structure. Go ahead.
I was saying you can randomly select state variable.
I would put at random. There is a requirement. They must be linearly independent. They must be linearly independent. Once you satisfy the condition, the minimum linearly independent variable, that is what constitutes the state variable. And one method to choose the state variable in this case is to choose the output, which is displacement, and the derivative of displacement, which is velocity. Those are two independent variables, and they are state variables. Okay?
And it shows mass, right? Or mass displacement. Okay. All right.
Okay. So I was asking the question, when we differentiate the second state variable, we end up with double dot x of t, which is acceleration. And I hope that we can see that acceleration is not a state variable. Our state variables are x of t and x dot of t. So as we have done in the previous example, we have to rewrite all variables that are not state variables in terms of state variables and input. Okay? So what would we need to do with x double dot of t?
Integrated.
No, we can't do that. If you integrate it, you would. All right, if you integrate it, you're actually changing its form. We want to put something there that represents it. What is x double dot of t equal to? That's what we really want to know. How would we get to that point? Anybody?
So the first derivative of velocity.
All right. Okay. I see. All right. No, I'm listening. But you see, what I want to bring your attention to. All right. You could go ahead and mute your mic. I'm getting some feedback. There needs to be a connection in terms of how you think. All right. Go ahead, Alman.
So it would just be x2 that.
Could you repeat, please?
It would just be x2 that or dot x2.
X2 dot.
Okay, isn't
All
x2
right.
the derivative of the first? So then x2 dot will be the second derivative.
No, man. Remember that we already have x2 dot here now. And it is equal to x double dot of t. Our challenge here is that x double dot of t is not a state variable. Hence, we have to find a replacement for it. What do we know about x double dot of t? Okay, so that when we remove it and place that new expression there, it is equivalent. Okay, what about this expression?
I feel like it's
Could,
not this.
could you use
Isn't this a law?
could you use f equal ma?
I'm bringing your attention to
So
the equation 1. Isn't it a law that governs the system? Yes? Yes or no? I'm not feeling the group this evening, you know.
sure.
Just like
Yes, it's a
Kirchhoff's
law.
law.
What, sir? What
I'm
I was
listening. Go
saying,
ahead.
sir, if we could use F equal ma, so acceleration would now be in terms of mass and force.
That F is equal to what? All right. What I
Now I'm
wanted to
saying
realize.
you wanted to replace the acceleration.
Yes. Go ahead.
Sorry, you just want us to use the
Yes,
function
sir. I
above
was
and
saying
transpose it to get x double dot.
But I would more importantly like you to realize why. Why? If you know that this system, it's the same thing with electrical network, you know. You derive a Kirchhoff voltage law. It's similar to Kirchhoff voltage law, you know. And if I said to you, what do we know about the current in the circuit? You would then go and look at any fundamental law that speak to it. So when I said to you, what do we know about acceleration specifically as it relates to the system? You have to go and look at the fundamental laws that govern that system. Okay? And so here is the law that we're speaking of. Oh, guess what? Acceleration is in the expression. So what do? We make acceleration the subject. Are we seeing that? So x doublet of t is equal to f of t over m minus c x dot of t over m minus k over m x of t. And that is exactly what we have right here. Right here. Are we seeing that?
Yes, sir.
Okay. Now, when we get to this point, we now again need to examine if this new expression has state variables only, and well, let me say it this way, have state variables and input function only. So let's step by step or component by component examine it. Is f of t a state variable? This is the first part. Is f of t a state variable? Is f of t a state variable?
no, sir.
Answer is no. No, it's not. So when you're doing your
Not.
calculations, make sure you write this down. See them there, you can always go back and look at them. And you look up there, you see x1 and you see x2. and x1 is not f of t, x2 is not f of t. So therefore, f of t is not a state variable. Do you agree?
Yes.
So therefore, we move on to the next test. Is f of t an input function? Is f of t an input function?
I would want to think so, sir.
Doubtful though. We already established that's the input. Didn't
Yes,
we?
sir. It is.
Absolutely, it is in the input. So it will stay then, right? Will it stay? Will that function stay? Yes, because we're expressing the state equation
No.
is written in terms of state variables and input function. So therefore, that part of the function can stay. Let's move to the second part of the function, k over m, that's negative k over m times x of t. Look for the variable. The variable is x of t. Is x of t a state variable? Is
Yes,
x
sir.
of t,
Definitely.
which one of them?
That's displacement.
No, man. Remember, the state variables are represented by x1, x2, and so forth. So when I say which one of them, you need to tell me if it's x1, x2, and yes? Is it x1 or x2?
Should be
X1 of t.
Should be x1.
It is in fact x1. See it there up here now. See it here. X of t is x1. Let's move on so that can stay. What about the other variable in this part here? It is x dot of t. Is x dot of t a state variable?
Yes, sir.
Watch which one?
x2.
X2. See it here? Therefore, we can rewrite equation 3 in the form of equation 3a, where we have x dot 2 equal u of t. Remember, u of t now is the input function over m minus k over m times x1 as we agreed, minus c over m times x2. That's it. Okay, that's it. So now we need to write it into matrix format. So I showed the last week how we moved to that stage. We're simply going to, we could group them in terms of x1, x2, and u in that order. All right, but let us look at, we could just write here. Let us look at it in this way. So look at x1 dot. This is, we'll look at the coefficient for x1, x2, and u. What is the coefficient of x1 in this expression here? Equation 2. What is the coefficient of x1? We're looking at equation 2.
Is it 1, sir?
I'm afraid I have to disagree. Is there x1 term in the expression?
Oh, no, sir.
No, sir.
Right, so we're simply writing back the expression in terms of x1 and x2. So there's no x1 term. So what we'll put? 0.
0.
Is there x2 term?
Yes, sir.
What's the coefficient?
1.
Thank you. Is there input term, u of t or f of t? Is there an input term?
No, sir.
So we'll put what? 0. Let's go to the other equation now down here. I'm doing the same thing, okay? We're doing the same thing. So we're going to look for, my apologies here. Oh, I just lost it. But what? I just skipped and lost it. So what you'd have seen is when we did our breakout, we saw we got 0 for x1, and 1 for x2. See there? And u was 0. The same would occur for the second part of the expression where we would break out the terms. So if we did the same thing, all right, for this part here, we ask the question, what is the coefficient of x1, x2, and u? Go ahead and tell me, please, in the order that I have it, x1, x2, and u. So x1 is x of t. Perhaps you could take it from here. It would be much easier here. So let's take it from here instead. What is the coefficient of x1?
Minus k over m.
All right, minus k over m. Continue for me. x2.
X2 will be minus c over m.
And the u of t?
U of t would be what? 1.
1 over m. 1 over m. All right, so let's go now. What just happened here a while ago? Okay, so let's go now to the expression and you will see what I'm talking about. See there? Is that okay? So that when you know expand, so basically what I've just showed you is how do you move from these equations into a matrix format. You have to put them in a particular form or structure so that you can now put it into the matrix format. That when you do what? Row, here's my pen, row by column, I'm sorry, by column here, you're going to get back what you had before. So what would we get? Let's do the first one. A little bit of time on this. x1 dot, we're expanding here. x1 dot is equal to 0 x1 plus 1. I'm just putting 1 so that you can see what I'm talking about. x2, what just happened here? x2 plus 0 u of t. All right. Now, what about the second part? x2 dot is equal to row by column again, minus k over m x1. This element times x2 is minus c over m x2 plus, this is now 1 over m u. Is that okay? So we expand the matrix, we get back what we had before in terms of the equation. Now let's move to the output equation. So we know y is equal to, let me make sure that we understand what this means. The output of the system is what? Mass displacement. Therefore, we can write y equal x of t. That's okay. Y is the output in terms of the state space model. Y is used to represent the output. Okay. Now, specifically to our system, what is the output variable? It is in fact mass displacement x of t. So that is why I put y equal x of t. Now we have to always express these equations in terms of state variables and input. So the usual question is x of t a state variable or an input function? And the answer is x of t is a state variable. It is in fact x1. Okay, so we can therefore express y is equal to x1. Now the same will apply. We have to do the breakout system again. We will ask the question, what is the coefficient of x1? The answer is 1, so we'll leave it like that. What is the coefficient of x2? It is 0. What is the coefficient of u, input function? There's none there, so we'll put 0 as well. In terms of a matrix format, y would be equal to, and you put 1 comma 0 to represent what is happening here, plus 0, yes, u of t. And this, of course, is going to be multiplied by x space, x. So this is our output equation. Do you recognize or do you appreciate the derivative of the output equation? Is it clear enough?
Yes, sir.
Okay, I hope so. All right, so we have so far looked at two systems, electrical system and a mechanical system. All right, and it's the same approach in terms of how we structure the state space equation. Now, when it comes on to mechanical system, it's always easy to choose the state variables in this fashion. All right, choose if the output is displacement, you could choose displacement and velocity or any other such independent variable. All right, go ahead, Richard. Question? See your hand up.
So the D equals zero. The D equals zero part. So what was that again?
You will call that y is equal to what? C x of t, and here x is the state vector now, right? Plus d u of t. Because the coefficient of u is 0, it therefore means that d is 0. Is that clear? I just wrote it here now. x1, x2, u. This is 1, this is 0, and this is 0. So when we when we expand our matrix, yes, what we'll get is row by column. We're going to get x1 plus 0 x2 plus 0 u of t. So d has to be 0. Is that okay?
Yes, sir. I saw a definition for D. I was trying to recall it, but I couldn't.
Feed forward matrix. In most of our examples that we look at, the feed forward matrix will be 0.
No.
I'm just telling you. All right. But I hope you can see why it is 0 in this analysis. That's the key thing to understand. Why is it 0 in this analysis?
Okay, sir.
All right. All right. So let us see if we can move on to the other section now. Now, we're going to look at how we can move from a state equation or move from a transfer function, to a state equation. Now, given that a system is defined by a differential equation of the form stated here, right? It's an nth order differential equation where y is the system output and u is the system input. Now, a convenient way to choose the state variables is to choose the output and its n minus 1 derivatives. Okay? So remember now, we're looking at an nth order differential equation. Therefore, how many state variables we need to have? N. How are we proposing to select them? Choose the output and n minus 1 derivatives. So the total here would be n state variables. Go ahead, Richard. Do you have a question? I see your hand up, Richard.
Was a mistake. I didn't. No, I didn't take up my hand as yet.
All right. So a convenient way to choose the state variable is to choose the output y of t and its n minus 1 derivatives as the state variables. So here we would satisfy the number of state variables required for the system, which is a total of n. Now, when we do it in this format, we call it the phase variable choice. Okay, phase variable choice. So here's what we end up with. we have selected our n state variables, and what you would recognize is that they are equal to the output and the n minus 1 derivatives. So this will be the first derivative, second, up to the n minus 1 derivative, which will give you a total of n state variables. Okay? Now, having done that, if we differentiate the state variables, what we would end up with is an expression that looks like this. So x1 dot would look like, I would probably go back to the previous slide and ask you to look at it. So when we differentiate, if we should differentiate x1, what do we get? So let's differentiate it. x1 dot, what is that equal to? It's equal to y dot. This is what we're focusing our attention on. Differentiate both sides, x1 dot equal y dot. What is y dot? It's equal to, look down here, x2. Let's move to the second part here. Now let's differentiate x2. x2 dot is equal to y double dot. Do you agree?
Double dot. Yes, sir.
What is y double dot equal to?
X3.
Equal to x3. I hope you can see the trend. Okay, so we keep doing that, and what we're going to end up with is what we have here. Okay, now having done that, we can now express this system, yes, in terms of state space model, and it will look like this, because we have now, remember we selected our state variables, you know. Let me go back to the previous slide. We selected our state variables and we differentiated them, because you must remember that the state equation is simply what? The derivative of the state vector. So you might be asking, why did I differentiate the state variables? Because the state equation is in fact the first derivative of the state vectors. That's just a simple answer to it. So once we differentiate these state variables, what we're actually looking at is the state equation. Okay? And we're now going to write it in the appropriate format, and it looks just like this. All right? That's it. So let us see if we could make sense of it. Row by column. x1 dot is going to be equal to what? Remember what it was equal to? Let's check it. 0 times x1 plus x2 plus 0 times everything else. Therefore, what we're saying is that x1 dot is equal to, talk to me, x2. Do you recall that?
Yes,
Yes.
sir.
Good. And it continues throughout. Okay? And we recall also that the output y was equal to x1. The output was equal to x1. All right? And so we will write the output equation in this way. All the other terms are 0. So you have 1, 0, 0, 0 all the way to the n multiplied by the state variables. All right, and in this case, d is also equal to 0. Let's look at the summary of how we're going to now move between or move from the transfer function to the state equation. What we're going to do is to, one, convert the transfer function, yes, to a differential equation. And we're going to do this by cross multiplying and taking the inverse Laplace transform. Then we're going to represent the differential equation in state space form, particularly phase variable form. Okay, let us see how that works out. So here is our system. It says find the state space representation in the phase variable form for the transfer function here. All right, g of s is equal to 24 divided by s cubed plus 9s squared plus 26s plus 24. That's a transfer function. All right. So what we're going to do, we are going to establish input and output and cross multiply. Now you recall that for a system, let's call it it's g of s in fact, there is an input. Let's call it input r of s, and output c of s. Is that okay? Therefore, we could say that g of s is equal to c of s over r of s. There we go. Okay. Now, it is quite okay for us to replace g of s with c of s over r of s. We should be fine with that. Okay. Now we're going to cross multiply. So what we're going to end up with is r of s times 24, c of s times everything here. And so we end up with this equation right here. The next step is to take the inverse Laplace. Okay, take the inverse Laplace. So while I may have omitted a step, I'm sure you can appreciate what is happening. So look at what we have to do first. We have to expand. We have to multiply c of s by each term in the polynomial here. So right here would have s cubed times c of s. Are we seeing that?
Yes, sir.
And when we take the inverse Laplace of s cubed times c of s, what do we get? We get the third derivative of c of t. See it right here? How about when we take the inverse Laplace of 9s squared times c of s? What do we get? 9 times the second derivative of c of t. I didn't put the t there because, well, you know, hope it is understood. How about 26s times c of s? It becomes the first derivative of c of t times 26. How about 24 times c of s? It becomes 24c of t. And over on the other side now, this part here, what's the inverse Laplace? 24 r of t. All right, so we now have a time domain function, and it's a third order system. Okay, it's a third order system. Therefore, how many state variables do we need? That's a question. How many state variables do we need? Go ahead, Bruce.
4.
So we
We
need
cannot. We need
three.
three. Thank you. We need three. We need three. Thanks. Three, because a third order system, we need 3 state variables. Now, my other question is this: how are we going to select the state variables? How are we going to select our? We need 3 of them. How are we going to select our state variables to achieve the outcome? Go ahead, Williams.
You would take the output as the first one, and you would have the 3 minus 1 derivative of that output.
So you're choosing the output as one, as
and
the first one, as you put it. What is the output again? What's the output variable? Correct. Therefore, you would have selected x1 equal c of t. What would be the second state variable? X2.
First derivative of c of t.
Correct. Correct. And the third one would be the third one would be c double dot of t. All right. So there we go. I actually jumped right ahead and start differentiating, but clearly you would hopefully see that we select our state variables. You should make a little bit more detail in the slide. But x1, as I said before, is c of t. All right, x2, the first derivative of c of t. Shifting x3, c double dot of t. That's it. Now, the next step is to differentiate the state variables. That should be understood now, that the state equation is just simply the first derivative of the state vector. And that is why we proceed to do that. What is x1 dot, x1 dot? Just simply differentiate. So I'm going to put a dot here, I'm going to put a dot here. But wait, let's look at this carefully. What is c dot of t? C dot of t is equal to x2. See down here already, we already have them, you know. It's equal to x2. Let's differentiate the other one. Dot here and dot here. Yes? Sorry, two dots now. Let's do this right. What is this equal to? Look down here. Equal to x3. Let's come down here. Put a dot. Put another dot here. It becomes triple dot now, right? Question is c triple dot of t a state variable? 3 dots. Answer is no. Therefore, we need to write c triple dot of t in terms of state variables and input. How do we do that? We have to go back to the differential equation and make c triple dot of t the subject. And that's exactly what was done here. Okay? So c triple dot of t is equal to minus 24x1 minus 26x2 minus 9x3 plus 24r. Okay? And so what we'd see here is that we have expressed x3 dot in terms of state variables and input. Yes? So we satisfy the expression. So we can now move from here to a matrix format. Okay? Let us do the same analysis again. Let's start with x1 dot. Again, let us go with x1, x2, x3, and u. What is the coefficient of x1 here? We're focusing on x1 dot. What is the coefficient of x1? Please open your mic and go ahead.
0.
It is 0. Continue, please. x2. Go ahead.
1.
It is 1. x3.
0.
0.
0. U of t.
0.
Taking a little while though, man. This is the only thing there's x2, you know. So everything else must be 0. So when you do it in this format, it is very easy to extract the matrix format. Because guess what? Look at the coefficients. 0, 1, 0, 0. See there? 0, 1, 0, 0. How about x2 dot? The only non-zero term is x3. And x3 is 1. So look at what's going to happen. x1 going to be 0. x2 going to be 0. And x3 going to be 1. And u be 0. There we go. How about the last term? Let me do the last term together. So the last term here is x1, x2, x3, and u. What is the coefficient of x1 in this equation? What's the coefficient of x1?
Minus 24.
Minus 24. Continue, please. How about x2? Minus 24. What about x2?
Minus 26.
Minus 26. Continue. x3.
Minus 9.
Minus 9. And you?
0.
0.
Really?
24.
Remember what the input was, you know? Remember the input was what? R, remember?
Yeah,
Do you
yeah,
remember
yeah.
that? So it is 24 plus 24. Now, all we need to do is just push this up into the matrix. See them, 24, negative 24, I'm sorry. Negative 26, minus 9, and the 24 for the input term. That's all we're doing. Okay. Now, for the output is actually equal to x1. And again, if we do the same thing that we've been doing before, hopefully by now we'll get the gist. This is going to be 1, everything else is going to be 0. Therefore, we can see it here, 0, 0, and then the D matrix is also equal to 0. So we have just converted the transfer function into state space form, and particular phase variable format. All right, any questions on that?
Sir, can I just...
Sorry, go ahead, please. There was a question.
Sir, I was saying if we can just go back to the reason or how we determined it was a third degree equation. Yeah, third order, yeah. Oh, okay. That's cube.
This, well, number of ways. It could be from up here, or it could be from here. This system is a transfer function, and the highest term in the polynomial is of third degree. The highest term in the polynomial, yes, is of the order 3. This is a frequency domain expression. Here we look at a differential equation. The highest derivative in the expression is third derivative. Are you seeing what I'm saying? So for transfer function, you look at the highest term in the polynomial. In the differential equation, you look at the highest derivative in the equation. Okay? All right.
Yes, sir, I got it.
Any other question before we move on to the other part? We're going to look at another type. Here we're looking at a transfer function now that has a polynomial in the numerator. Same treatment. What we're going to do, though, is we're going to break out this system. All right, we have this. We need to know. We need to create a state space model for this system here. And so we could put this in a block, and we know that R of S, Y of S is our input and output respectively. So to make things simple, what we're going to do is to break out this system into 2 systems. We're simply, taking, and hopefully we can see this. We're taking the denominator, we're taking the numerator, separate them. Of course, in blocks in Cascade, it comes back to the same thing. So it's equivalent. Do you agree? It's equivalent.
Yes, sir. Yeah.
Good. And we see that the input of the system is R of S and output is Y of S. And we just simply choose any other expression for the intermediate signal here. We're choosing W of S. What we're going to do is apply the rule to this part of the system first, and then this part, and then join them. So let's proceed. For the first subsystem, we have this one here. Remember that the output is W of S, right? I need to remind you that the output is W of S. See here? That's the output, W of S. So we're now going to write W of S over R of S is going to be equal to what we have inside here. So there we go. Do you agree with this? W of S over R of S is equal to the 1 over S cubed plus 9S squared plus 26S plus 24. That's fine. For the second part of the system, we agree that y of s over w of s is equal to s squared plus 7s plus 2. All right. Now, what we're going to do, let's start with the first one. We are going to now cross multiply. And when we cross multiply, we're going to take the inverse Laplace. So I'm actually doing two things at the same time here in one step. So I cross multiply, what would we get? We'll get ws times s cubed plus ws times 9s squared plus ws times 26s plus ws times 24. 24, good, equal to r of s. And when we take the inverse Laplace, we can see that the s cubed times w of s will give us w of t in the third derivative. Make sure I have that correct here. Correct, here we go, right here. Is that understood? How about 9s times w of s? When we take the inverse Laplace, look at the s squared here. It will be the double derivative. So we end up with 9 times w of t to the second derivative, actually. See here? 26s times w of s will give us 26 times first derivative of w of t. Here we go. How about the w of s times 24? Just simply give us w of t times 24. And the other part of the equation now, which is r of s times 1, inverse Laplace just becomes r of t. There we go. Is this part clear? Any questions on that?
Yes, sir.
Okay. So we do the same thing for this part as well. We cross multiply and take the inverse Laplace. All right. So I'm not going to go through the steps again as I did before, but I think that you understand how to get the inverse Laplace. Okay. So now move to the second step now, which is to now choose the state variables. Before I go to the second data slide, how then would you choose your state variables? What would be your state variables? Let's focus our attention on this one.
For the
What
first
would be
one,
your state variables?
for the first one would be the output, would be one of them, which would be,
Which is
I think,
what?
WS.
Correct. No, it's not WS anymore. It's W of T. We know in time domain.
Okay, WFT.
So, yes, that would be the output. And so that would be our first state variable. What would be the second one?
The differential of WFT.
Correct. And the third?
The second differential of WFT.
All right, good. That's exactly what would have happened. So here we select our state, thank you. We select our state variables. X1 is W of T. And again, I didn't put W of T, just that we understood that. X2, double dot of T, I have X2 twice. It's supposed to be X3. And I have it quite a few times. All right, so please note that this is not X2, it's X3. And this is X dot 3 as well. All right, so I'll seek to correct into my upload the updated slide. All right, so we have selected our state variables, and we now move to do what? Find the first derivative of the state variables. Now, again, it's a similar thing will happen all the time. See that the third derivative of W is not a state variable. Check out right here. It's not up there. Therefore, we have to express the third derivative of W as in terms of state variables and inputs. And that's not difficult. We just go back to the equation that we had before, and we make the third derivative of W the subject, and this is what we end up with. Now, when we look at this expression, we can see that all the elements, let's come here, all the elements are in fact state variables and input. This is a state variable, this is a state variable, this is a state variable, and this is an input. Specifically, you have X3, X2, X1, and R. Okay? So that's where we're at. Go ahead with the question.
So I just wanted to see how you got the third derivative to be expressed in terms of the state variables. How did you get to?
You remember this? I'm sorry, not that one. This one. Do you remember that one?
Okay, yeah.
So if you make this the subject, it becomes 9 double derivative of w plus 26 derivative of w plus 24 w. I'm sorry, let me go again to this. We're simply taking all the terms here and putting them on the opposite side of the equal sign, which is the r minus 9w second derivative minus 26 first derivative of w minus 24 w of t. Exactly what we have right here. Is that okay?
Oh, yeah, yes, sir. Good.
All right. So from there, it is a simple matter of taking out the coefficients. Again, only if you look at, if I should start to do it here, right? And this is going to be x1, x2, x3, and this is going to be plus, oh gosh, and u of t going to be there. We can see for this one, 0, 1, 0. Down here, 0, 0, 1. By the way, let's go across. 0 up here, 0 up here. The last line now, look for the coefficient. x1 is minus 4. Minus 4. What's x2? Minus 26. What's x3? Minus 9. What's u of t? 1. Are we seeing that? Or we extract the terms. There we go. Right? There we go right here. And recall that y is equal to the output. What's the output?
W of t.
Equal to w. And it is equal to x1. So it look like this. Okay. So now we're not finished. We just simply look at the state model of a G1. Question is then, how do we then make it into one expression? Recall that y of t, yes, the ultimate output of the system is equal to what we have right here. And I can go back and show you that. Let's go back to, here we go. See there? Oops, let's do this correctly. See there? That's what y of t is equal to. And you'll also recall that y of t is the time domain output of our system. Okay? So let's go back to that expression now, where we're saying, yes, we know that y of t is equal to what we have here. And so it's a matter of expressing this in terms of state variables and input. What do we know about double dot, about the second derivative of w? It is equal to x3. What about the first derivative of w? Equal to x2. What about w? It's equal to x1. We all know this is already written down as the state variables. So we can now replace these terms with x1, x2, x3 as we just did right here. And it can now be placed into the output equation. Hence, our output equation is now this expression here. Is that okay?
Yes, sir.
Okay. Anybody else have a concern or a question want to ask?
No, sir.
All right, so, all right, good. So we're going to continue then. All right, so we're going to now look at how we move from state space to transfer function. And in this course or module, we're not going to look at any system beyond second order or above second order. Okay, just the basics. MATLAB, the software MATLAB does this quite easily, and the purpose of us doing it here is to get an appreciation for what is involved. But the truth is, nobody go by first-hand principle in doing these conversions. Systems are usually very complex and best done by software. But again, it's appreciation for what is involved. All right, so we're going from state space now to transfer function. Here again, we have what? The general expression for a state space model. What I'm saying here now is that the transfer function, which is output over input in the S domain, S, C of S over R of S is equal to, here is the, you like to talk about formulas. Here is the expression. It's C times everything in bracket, Si minus A, the inverse of that, times B plus D. Okay, where I is the identity matrix for A. Okay, so let us proceed to look at an example. All right, so I have an example here. Here we have a state space model. I'll respond to the question. I see Alan asking a question about tests. If this is done a test, we'll discuss the test in the last couple of minutes of this presentation. Remind me if I don't do so. Right, so here we are going to apply the rule. All right, so let's look back at the expression again for what we're looking for. It's C times S times I, that's the identity matrix for A, minus A, all, we find the inverse, times B plus D. Not so difficult as it looks, all right? So let us proceed to do this. And we're going to do what's in bracket first. So our first step is to look at the matrix. And we know that the matrix has A here, B here, C, and D equal what? 0. All right. So what is SI? All right. What is SI equal to? S times the identity matrix. All right, let's do it this way. Here is the identity matrix. What's the result of that?
S0, 0S.
All right, thank you. All right, so that's the first part. No, it's still coming up. So Si minus A now. So we have to come back to what A is. So we have come on, 0 S0. All right, minus A. Remember what A was? Let's go back to see what A was. A is 0, 1, minus 3, minus 4. Oops, wrong direction. 0, 1, 3, 4. Oops, I lost my annotation. All right, so what happened here is that when we subtract Si minus A, we're going to get this expression here. And just simply matrix addition, okay? Si, which is S times the identity matrix, minus A. All right, and we're going to end up with this expression. Now from there, all right, can you remind me of the expression? Let me write it for you. C, get my pen. C S I minus A inverse times B. All right. Okay. And now D is equal to 0. So we're going to find the inverse of this expression here now. Do you recall how to find the inverse of a 2 by 2 matrix? The inverse of a 2 by 2 matrix. I'm not getting any response from the crew. Go ahead, Burns.
Yes, sir. Is it 1 over the determinant times the adjoint?
Okay. So do you lot of feedback. So the determinant is what now? How do we find the determinant?
Multiply S with S plus 4 and minus 3 times minus 1.
Okay. And this works out to be it?
Yes, sir. S
And then you know what?
plus 2.
And then we now do some manipulation with the matrix here, with this actual part here. Where's my pen? What do we do with that part of the matrix? We switch something up. What do we switch?
We switch S with S plus 4 and
That's the
we
leading
change
diagonal,
this.
right? So we switch the elements in the leading diagonal, and then we do what with the other diagonal?
Change the signs
Good.
of the other
And
diagonals.
so, good. And so that's how we find the inverse of this. This is it right here. All right. And the next step now is to multiply it by b. All right, let me. We're multiplying it by b. And let me bring you back to what b is. So b here, the matrix 10 and 0 itself. 1 by 2. So when we come over here, we're gonna, we actually did the multiplication here. So what should be here is actually CSI minus A times B. If you recognize that we actually multiplied by B already. Are we seeing that? I need to edit this slide. All right, are we seeing that? So we actually did the multiplication by B here. All right, so you would put this one side and you focus on the matrix. All right, so this would be this part here multiplied by, is it 10 and 0? Let me just go back and check again. 10 and 0. So this part here multiplied by 10, 0. All right, so it's rho. Let's do this correct now. CSI times that. Let's see, did I do? No. B. Nobody said that wasn't B? Nobody saw that wasn't B? What is B? So remember A, B, C. You want to sleep on me. All right. Okay. So let me make sure I'm not making a mistake here. So we did CSI. All right, let me scroll a little bit. Let's go back. Let's go back. All right, let's go back. So SI minus A is established here. Okay. Now we find the inverse. This is the inverse right here. All right. Now the next step is to multiply the inverse of SI minus A by C. And C is actually 10, 0. So if we apply this vector or matrix to here, row by column, 10 times S plus 4 plus 0, 1, and they have 10 row by column again. Let's do this again, row by column. So it's 10 times S plus 3 plus negative 3 times 0. So that's going to be 0. Then you have row by column again. So it's 10 times 1 plus 0. Here we go. That's okay. And then the last step now is to multiply by B. And recall that B is, this is going to go now. Just bear when I go back to B. So B here, B is 0, 1. So 2 by 1. right? And so this would be the result of the conversion. Is there an aspect of this that is not clear? Go ahead, Richard.
Sir,
Yes, go ahead.
Yes.
the second line.
Second line, what about the second line?
When you multiply C with the inverse, right? What you did, you converted the inverse back to matrix form and multiply it, or you converted
No. You see this part here? Where's my pen? I think I lost my pen. The power in my pen just went. All right. Give me a few seconds. What I did, you take out the polynomial here and work with the matrix. So it will be, you'll be multiplying this by what is here.
Oh, okay. Yes,
so
sir.
row by
Understood.
column. All right, row by column. And then when you finish, you just put back the polynomial before whatever you get, which is what is happening here. Are we seeing that?
Yes, sir. Yes,
Okay.
sir.
All right, noted. Another question? All right, and so we proceed to do the same thing. We multiply what we have up here, yes, by the last term or the last matrix, which is B, and we end up with our transfer function. Okay. Now, of course, you can work back from here to state space, and it will look different. If you use the phase variable format, it will look different. But when you do simulations, you will see get the same output response. It looks different, but the dynamic response in simulation is the same. All right. All right. So this aspect of it, I will not be testing on it per se. All right. And you might ask, why did I put it there then? I'm not testing on it, but I'm just putting it here just a few minutes to talk about it. Discrete time systems, all right? A system is a continuous time system if it's analog, right? And here we're talking about the variations of the variables having a continuous variation. There's no breaking there's a continuation in the variation, all right? That's what we call analog systems or continuous time systems. Now, physical systems, I call them plants, are continuous time systems. Now, for computer simulation or control, the continuous time plant, right, that model must be approximated to a discrete time system. Right? As you know, your computer don't process things continuously. I hope you all know that, right? But it processes things in terms of discrete times. Right? So one method of designing a digital controller is to design a continuous time controller and then approximate the controller into discrete time. So what I'm saying here is that the continuous time function will not give us the same result as a discrete time signal. And so there is the need for a modification of the model. Perhaps this diagram will help us to appreciate that. You have a computer, and the computer needs to send a signal to a plant. A plant is something in our physical environment. It could be the current going to a motor. Of course, the signal from a computer is discrete. So that has to be now put in a digital format or converted to an analog representation with the use of a what? A DAC. Okay. Now, when it is that the computer needs to recognize what is happening to our motor, it needs now to use a special device called an ADC to convert this analog signal back into some digital format. So what am I focusing our attention here on? the signals are discrete. Look at this clock here. This clock will take the samples of signals coming from your computer as well as signals going to the computer. It's discrete, right? It's discrete. All right, so this is demonstrating the nature of digital control systems. Now, the response of a system represented in continuous state space can be obtained by discrete time approximation. Okay? Now, the time approximation is based on the division of the time axis into sufficiently small increments. What am I saying? If you take your samples really, really, really fast, then you're getting closer and closer to what is represented in the continuous time. Okay, so that's the essence of what I'm saying here in terms of our discrete time evaluation. And we could look at a model. We won't even go back past this page, but what I'm focusing our attention here is on that most of our systems that we have today, they're digital control systems. All right, and even though we have a state space model that speaks to continuous time, there is a special model, space-based model, that takes into account the discrete nature of signals that we would be using with a computer. All right, so I'm going to stop here. This will complete the presentation for today. I see a question in the chat relating to tests. Would you want to share your concern, Michael? But his mic is open. Is it Michael's? Is Michael still with us? All right, go ahead, Christoph.
Sure. Do you normally have a class Wednesday 3?
Wednesday at 3. There is a schedule there. Is everyone seeing that time there for tutorials? My understanding that some persons weren't seeing that slot. Hello?
Yes,
Sir, it's
because
not on my timetable.
it's affecting my module selection, sir. So I'm wondering if I can change that via
That's
admin.
tricky. We have about maybe 40 students in the group, and my side it's not easy to change unless you can propose as a group another time.
No, I'm
You know.
if you have a class, you normally have a class during that period.
I'm saying it's on my timetable, but there are persons who are not seeing it on theirs. So my question is, are you seeing it on yours?
Yes, I'm seeing it, so, and it's affecting my selection process. So I'm wondering if
Is there a clash?
Yes, there's a clash.
Fine. So therefore, there's an issue with that time slot for tutorials for you. I don't know, maybe that other person having a similar situation. But as it relates to the test, before I stop the recording, I just want to make it clear for persons who may not be on. The test, I'm going to post the topics that the test will cover. The test will cover elements of the, tell you what, I'm going to post the content. All right, it will cover some of what we did in the, what's that, unit 2 or lecture 2, and move over into this presentation. The tutorials will guide you. I'm going to post additional work if needs be. By the way, did anybody look at the tutorial sheets?
I looked at the first two, sir.
So, would it be okay? I should even ask this question because I might get no. But I'm proposing to have the assessment done up to conversion between state space and transfer function. That is what I'm proposing up to this point. Right?
Yes, sir.
So
And that came.
Okay,
Yeah,
sir.
go ahead with the question.
that's not a problem, sir. But I came on late, so I'm wondering if the test is scheduled for next week.
All right. What I would like for you to do, you see, is when
Right.
you go on this on the portal, you look for the calendar, and whatever you see there will maintain unless there is some unforeseen situation and I inform you in advance.
Oh,
So
okay.
if you see a test there for next week, there will be a test next week. That okay?
Yes, sir.
All right, cool. All right, so I'm gonna stop the recording now.